Hello everyone. Today I'm going to talk about manipulator kinematics and trajectory planning. This is the unit number 4 in artificial intelligence and robotics subject. For understanding this particular unit, we need a prerequisite from unit number 2 about the basic configuration of robot and robot actuator, and unit number 5, the robotic application. So for path planning and obstacle avoidance, if I am explaining with some real example or real application, it would be more understandable. Therefore, I completed unit number 5 before. The syllabus for this particular unit is the various topics, two major topics: manipulator kinematics and trajectory planning. Manipulator kinematics, we have a mathematical representation of position and orientation, homogeneous transformation, DH notation, forward and inward kinematics, and differential transformation, Jacobian. The trajectory planning topics includes trajectory planning, avoidance of obstacle, path planning, joint integrated motion, for example, straight line, and other motions also important. So I'm going to discuss and the basics of trajectory planning and the polynomial trajectory planning. So here avoidance of obstacle I'm going to talk at the end. So after explaining all the planning, then how the avoidance of obstacle we are planning in our system. Your unit, it is connected with the robot manipulator. So first of all, so I need to explain what is manipulator. So it is a prerequisite. Manipulator, it is like a structure like arm in an industrial robot, and this component is completely taking care the task given to the robot. It is also known as a robot arm. Manipulator mounts to robot body and consists of multiple links and joints. Next to the links and rigid components that connect different sections of the robotic arm. Their rigidity provides solid structure, but joints are necessary for flexibility. So flexible to move one point to another point. As with the human body, robotic joint move different ways, facilitating various movements such as linear, rotary, and revolutionary movements. This allows the robot to perform the desired movement within the work envelope. So this is the simple prerequisite to understand what is robot manipulator, how it works. So next, so I'm going to talk about the robot configuration. So this is already we have seen in unit number 2 clearly. This is the typical shape for robot structure. So already we discussed the links and joints. So here link 0, link 1, link 2, link 3, and again joints, right? It is available, different links. Finally, this particular place is called end effector. The whole system, it is called as a manipulator, including the end effector. So here it is clearly available: joint 1, joint 2, joint 3, joint 4, joint 5. So different joint 7, different joints are available. So this slide I'm clearly explained what is link, what is joint. And here in between the joint, the it starts from beginning. It is called joint origin. So this place it is called the joint origin. Some textbook it is referred as the parent. This is the parent link. This is the child link, right? So now coming to the theory, the kinematics of manipulator refers to all the geometrical and time-based properties of the various movement. Here, we are clearly explaining that the relationship between these movements, these motions, the force and torque that generated them to constitute the problem of dynamics. Now I am coming to, I start with the formal introduction. So introduction in the sense, some of the prerequisites required. A robot manipulator is designed to perform a task in 3D space. So this is the known fact we are discussed in unit number 2 also. The tool or end effector are required to follow the planned trajectory. So this is the end effector is the end point of the robot. Previously we discussed that need to follow the planned trajectory to carry out the task in the workspace. The kinematic model describes spatial motion of joint and link, position, orientation of the end effector. So spatial position of various joints. So different joints we have seen in preview, shown in previous slide, and similarly links, position and orientation of the interfactor. So the position orientation of interfactor also, it is important to describe a kinematic model of the robot. The motion can be either unconstrained and constrained. If it is unconstrained, there is no physical interaction between the end effector and the environment. There is no end effector. There is no physical interaction between the end effector and the environment. Therefore, the motion, it will be freely taken care. So there is no obstacles, nothing. Straight away they can carry. If it is a constraint, if contact force arises between the end effector and the environment. Next, I am going to the kinematic analysis. So this is a prerequisite to understand further. So therefore, I am discussing here. The kinematic analysis of manipulator structure consists of description of manipulator motion with respect to fixed reference. For example, if you want to describe anything, this reference is important. With respect to reference, how it is going on. This is the way we will describing the various moments. The Cartesian frame by ignoring forces and the moment that cause motion of the structure. So Cartesian, the structure, so unit number 2 clearly described, it's only linear movement, there is no angular. The kinematics also describe the analytical relationship between the joint position and end effector position and orientation. So joint position and end effector position and orientation. So this is the basic relationship is required to perform the task. The formulation of kinematic relationship allows studying two key problems. One is the direct kinematics problem, which concerned with the determination of systematic general method to describe end effector position and orientation as a function of joint value, right? Joint value, right? Another one is the inverse kinematics problem. It is just reverse. Transform a description and the orientation of end effector in the workplace into corresponding joint values. So this detailed explanation, forward kinematics, inverse kinematics, we are going to study detailedly with a real-time example. The differential kinematics describes analytical relationship between joint motion and end effector. This is already we discussed. In terms of velocities, right? Velocities, you have a statics, dynamics. You know the basic difference between statics. So here, to determine the relationship, forces torque applied to the joint, forces moment applied to end effector in static equilibrium configuration. Whereas here it is in dynamic movement. Okay, the equation of motion in dynamics, the equation of motion of manipulator as a function of forces, moment acting on it. The availability of dynamic model is very useful mechanical design and the structure. The choice of actuator. So here I said that the actuator, it is in unit number 2 that prerequisite we have to recall to understand. Determination of control strategy, computer simulation of manipulator motion. The object location, it is a robotic manipulation. By definition, it implies that parts and tools will be moved around the space by some sort of mechanism. So we are using different types of mechanism. Here, this is naturally need to representing position and orientation. That is a location of parts, tools, and the mechanism itself. And it is also defined the manipulate the mathematical quantities which represent the position orientation. We must define coordinate system and develop convention for representation system. This slide, we clearly understand that need for representing position, that is the location, that is the first thing. Manipulate the mathematical quantity, that is the key. With here, we need to define the coordinate system. So coordinate system means x, y, z, all the coordinate system for representing. Next, Cartesian coordinates. Cartesian means unit number 2, you have a clear prerequisite that there is no movements are connected. So it will be a linear movement with respect to x-axis, y-axis, z-axis. I clearly explained during the unit number 2. X-axis, right to left, right? X plus x minus, right to left respectively. Then y-axis, front, back. Front is positive, back is negative. And z-axis is up and down. Up is positive, down is negative. So I hope this one you can able to recall now. The position of the object in the space described with the Cartesian coordinate. In robotics, chosen coordinate frame forms right-handed set of vectors. So this right-hand of sector, it is available in the next slide by seeing that the positive direction of rotation is chosen accordance with the right-hand rule. This is clearly described. So here this is aligned. Look at this is X, this is Z, up and down movement Z. Here Y it is available here. You look at the here of here if you put the coordinate system here, you will get the X, Y, Z. So this is represented. All are mutually perpendicular. That story we know. Here right hand rule in the sense when it become positive. So rotation, clockwise and anti-clockwise movement. You look at this movement, it is a anti-clockwise movement. They are considering anti-clockwise movement as a positive, clockwise as a negative, how it is rotating. Here in text clearly given coordinate frame showing positive direction of axis according to the right hand rule. So based on right hand rule, they are doing. Next, I am coming to describe the description of question. So this is the one of the syllabus topic here. A point in space can be described with the coordinate system. Coordinate system means x, y, z. X, y, z. For example, if you want to locate a position, what is required in space? We are taking a origin starting point. What is called reference point? We discussed previously from the reference point, right? We are taking a reference point. That point, how much distance from x-axis, y-axis, z-axis. So this is the typical description of the question. For example, here x, y, z, it is clearly mentioned here. X direction, y direction, z direction. Here, position vector point P is there. Here, how they are representing. So this is available in next slide. In the above figure, the position point AP is vector origin of coordinate system A. So coordinate system A origin and the position vector can be represented in the homogeneous coordinate system, coordinate as a vector. This is called homogeneous description. So anyway, further explanation it is coming in next. As here, so this position, if you want to put it into the form of matrix in the form of coordinate system, px, py, pz. That means that point P where how much distance from x-axis, y-axis, and z-axis. Further, now we are describing the position. Now we are going to talk about the orientation. So position it is okay. Orientation means how to represent. So we will find not only represent the point in space, but also describe the orientation of the body in space. This is important. Really, while talking about end effector in this space, the orientation is very important. Position and orientation both are very important to control the system. For example, a box can be oriented arbitrarily while keeping the corner in the same position in the space. In order to describe the orientation of the body, we will attach the coordinate system up to the body. Then give a description of this coordinate system related to the reference system. So if you make a reference system to put a position and orientation at the single, here you look at that. You have a XYZ is there. Here you have a XYZ is there. Here A is the initial position. So AP is the vector. So that is moving from point A to B. So this is the way we have to represent. Here now the from the sketch we need to understand the coordinate system B has been attached to one of the corner of the box. That B here it is in corner it is attached, and the description of B with relative to A now it is gives orientation of the body from where to where it is moving. So position of the point are described with the vector, orientation of body described with an attached coordinate system. So only way to describe body attached system B is to write the unit vector of three principal axes, that is x, y, z of the coordinate system of A. Suppose if you put a 3 into 3 matrix described below, it is called a rotation matrix. And because of particular described B related to A. So the rotation matrix, if you want to put it, so rotation, that symbol R indicates rotation. So rotation A to B, it is described like this. So XB, YB, ZB, these are all coordinated. A is constant. In summary, it is three vectors may be used to specify the orientation. So next we are going to talk about for our convenience, if you want to construct a 3 into 3 matrix, position of the point represented by vector, orientation of the body represented by the matrix. So here B relative given, this is the equations they are giving. So this is the inverse rotation of the matrix. So inverse rotation we are going to talk later. Now we are going to talk about the rotation. So rotation we spoke in previous slide. The rotation it is possible with respect to x-axis, y-axis, z-axis. The rotation it is possible clockwise movement and anti-clockwise movement. So right hand corner rule which very clearly describes that rotating right hand rule. So that is anti-clockwise is positive, clockwise is negative. So let us see rotation of z-axis, x-axis, y-axis, how we are going to represent in terms of matrix. That is important. So here note it is clearly given the axis that is pointing out of the paper denoted this, and axis that is pointing out to paper denoted by y. Right now I think we rotation about the z-axis. Right, it is clearly given z0 and z1. If it rotation means at what angle it is rotating, right? What angle it is rotating. For example, if rotates theta degree, x naught, y naught is the initial position. Now after rotation, it will move to x1 position and y1 position. So therefore, overall the orientation it will start from z0 to z1. So here it is clearly given, right? Point of paper axis. Next, for this, if you want to put it into the matrix form, you will get it rotation 0 to 1, cos theta minus sin theta, cos theta. This is usually available. So this is the z-axis. So where is the z-axis component? Here x, y, z. Here x, y, z. So look at both the z components are it is not changed. Okay. Now cos theta minus sin theta, cos theta. Z-axis elements are 0, 0, 1 like this. The diagonal always 1, so remaining it will be 0. If you go for x-axis rotation, right, x naught, x1, here it is moving from y naught to y1, z naught to z1. If you want to put the matrix for this is x-axis. So x-axis, this and this are connected. So diagonal you will have a one value. Remaining all are 0. You put same cos theta minus sin theta, cos theta. So previously here z-axis we left, but here this is the x-axis. Therefore here you put it 0. Diagonal 1, remaining all are 0. The x-axis you will get cos theta sin minus sin theta, cos theta. Rotation about y-axis. So y naught, y1 is available here. It is rotation. Now movement from x naught to x1, z naught to z1. For this, if you want to make a representation, y means always it will be at middle. X, y, z, y is the middle element. So middle element you put a diagonal 1 and the remaining all are 0. Same thing, cos theta, minus sin theta, cos theta. So this is the way you have to represent the rotation of x-axis, y-axis and z-axis. Right. So now in robotics, the homogeneous transformation matrix have been used as a tool describing position and orientation. So describing position, orientation, if it makes a linear movement, rotary movement, how to put it in matrix. So everything we got information now. So the homogeneous transformation matrix can act as a vector or a frame that displays. So robot movement, there are two movements are possible. One is translation and rotation, what is called displacement. Then t equal to r comma p can be expressed as a t, rotation, omega, theta and p. Here you can act on a vector or frame and rotate it by theta. So theta is an angle and rotating about with angular velocity of omega. So rotating means you are giving some speed, angular velocity, like revolution per minute, like that. And again, it will translate into P. So clearly rotation, they are bringing all the elements. For example, rotation at a theta angle with a angular velocity of omega. If you make a rotation, the linear translation, you will get P. Now I am coming to the homogeneous transformation of matrix. This is one of the topic in our syllabus, that means unit 4 syllabus. Transformation matrix must be in square form. So you have to represent either 2 into 2 or 3 into 3 or 4 into 4. It must be easier to calculate a inverse square of matrix. So to multiply two matrix, their dimension must match. So this is the reason why we are using square matrix 2 into 2, 3 into 3 like that. Representation of pure translation. Here, translation is defined making a movement in space. Pure translation, pure rotation about the axis. Sometimes we will go for combination of rotation and translation. Now, representation of pure translation in space. Translation means, it's completely linear movement. You have a x, y, z. So initial position, right, A, O, N, A, O, N. So with the distance of D. For the representation in space, we are writing into that matrix. So last one, it will talk about distance traveled. It is a square matrix, diagonal always 1. So here they are representing the dx, dy, dz. So the translation with respect to x-axis, y-axis and z-axis are marked, right? This is a square matrix. And representation of pure rotation about its axis. If you want to make a pure rotation, so initially you have a xyz axis is there, point P is there. If it make a rotation, so with the P, before rotation, it will make a px distance from x-axis, this distance from y-axis, it is already there. After rotation, it will be like this, right? After rotation, here you look at certain angle of theta, right? Initially available here, this position, and it is making certain angle. This can be represented like this. In case if it is a 4 into 4, how to make a homogeneous transformation? How to make a homogeneous transformation? Um, Here you take same thing, rotation about x-axis with respect to theta, 4 into 4 matrix. The last column always 0, 0, 0, 1, 0, 0, 1. So remaining 3, it will vary. So this one previously I clearly explained. If it is a x, how it will be. If it is a y, how it will be. If it is a z, how it will be. Okay, the here 0, 0, 1, 0, 0, 1. This will be constant. Remaining 3 into 3, you have to make changes. Okay, this representation already we discussed. Suppose if you want to go for rotation about x comma theta, that means x comma theta, rotation about y comma theta. So this will be the translation matrix 4 into 4. It will be defined as the A, B, C. So this is the distance, right? Translation. Translation means linear distance. Here you write as usual matrix 3 into 3 matrix, right? 1 0 0 1 0 0 0 1. So this is 3 into 3 matrix traditional. Here as usually you put it in place of this 3 0, you will put the translation with respect to x-axis, y-axis, z-axis we are marking. So this is the homogeneous transformation. Next, I am coming to the direct kinetics manipulator and inverse kinetic manipulator. Previously, we came, just started what is meant by direct and inverse kinematics, how it will work. Here, to solve the direct kinematic task manipulator, the position of the gripper tool, center point, and gripper tool are orientation coordinates in the base are calculated if joint angles are measured by the drive sensor or known joint coordinate. In other words, gripper and tool location is calculated according to the measured angle of manipulator joint. Right, angle measurement. They are putting some drive sensor, right, some displacement sensor. We are marking the angular displacement sensor we will place and use. Similarly, inverse kinematics means whatever we are output we are getting, that will be the input. So input it become output. Uh, so here I am going to explain very clearly the difference direct versus inverse kinematics. The basic difference is first I will come here. So initially, if you are inverse forward kinematics means if you have a joint angle means theta 1, theta 2, theta 3. If you know, you will able to find the position x, y, z. Okay, in forward kinematics. Whereas inverse kinematics, you know the position, right, x, y, z value. In inverse kinematics, what to do? Your requirement will be joint angle. Okay, forward kinetics, what is input? Joint angle input, position output. Inverse kinematics, position is the input, joint angle is the output. So here you look at it is clearly given in text. The joint angles and links are geometry that is given. So we have to compute position and orientation of the end effector. End effector means this position related to the base frame. Whereas inverse kinematics, position orientation of the end effector value, it is given. It is already with us. We have to complete all possible set of joint angles and link geometry which could be used to attain the given position and orientation of the end effector. So this is the difference. I think you can write more about this picture and this. Here it is clearly given. Inverse kinematic task manipulator, the all manipulator joint coordinates is calculated. If the gripper or tool reference position and orientation angle are calculated trajectory planar in the base world Cartesian coordinate, right? So once if you known the example, so it is clearly given the basic difference. So we can understand what is it. Next, I am moving to, I am going to explain with this sketch, forward kinematics, inverse kinematics, which is important topics in this particular unit number 4. Therefore, I want to explain very clearly with the sketch. Right here, taking one real-time example. Here you have a body, shoulder, elbow, forearm. This is the link 1, link 2, link 3. Right. This is a joint 1, base joint 1, joint 2, joint 3, finding the position and orientation of the point from the joint angle finding. So the joint angle, everything you know, right? By using forward kinematics, you can able to find out the position and orientation. But here the requirement is different. Orientation is known. By keeping orientation, you have to identify, you have to determine the what is the joint angle and link dimension, everything, right? So here it is inverse kinematics. It is clearly available. Look at how the arrow marks going. Theta 1, theta 2, theta 3 input, and finally orientation they are estimating. Here it is clearly available. Position orientation it is available. That is the input. They are estimating theta 1, theta 2, theta 3. So this is the difference. I think you can explain detailedly based on this sketch. Next, I am coming to DH representation. This is also an important topic. It is developed by Denwitt and Hartenberg. So generally, it is called as a DH representation. Representation in the robot end effector. Both are developed a general theory to describe an articulate sequence of joint. So your robot connected with the links joints together. Here they are simplifying to describe the various joints and everything. Here, what they are doing means you have many movements are there. They are considering only 4 parameter. Each joint in the robot is described by 4 parameter. Next slide, we are going to talk about what are the 4 parameters. How remaining parameters are left. We need 6 degrees of freedom. Keeping 4 parameters, how we can describe. For example, you take a serial link manipulator, you take a two link manipulator. So this is the link 0 initial joint and the link 1, link 2, right? Link 1. Here you have joint 1, joint 2. For this, if you want to represent, if you want to make a DH representation, each joint is attached via link. The links are rigid. Joint can move either revolute or prismatic. Joint it can move either rotary movement or linear movement. Every joint connects two links. For example, joint 2 is there, you have two links. Okay. Joint 1 is there, you have link 0, link 1, both are there. Every joint connects two links. Every link connects two joints, right? Two joints, except first and last. Okay, because here n joints are there, always the link become n plus 1, not less than that. So this condition should be implied this. Now we are going to talk about uh, y4 parameters. So previously DHA representation, we are considering 4 parameter. The remaining 2 parameter, how we are ignoring. So that is important thing we need to understand. If you take any movement, you have 3 translation, 3 rotation. You know that basically available. 3 translation means movement with respect to x, y, z. Rotation means rotating about x, y, z. For DH notation, if you want to give it, look at this picture. Here you have link j minus 1, link joint j, link j, joint j plus 1. Here you have an end effector. Okay, they are taking this particular link. This particular link, you look at the here x minus 1, z xi, yi, zj, it is available. Here you look at that xj minus 4, xj minus 1, zj minus 1, because this is the basic link. Next, if you look at that x, y, z, So this is the representation. Here you look at that axis xj intersects zj minus 1. Axis xj, here you have xj, it will intersect the at zj minus 1. So intersecting, both points are intersecting. It is coming here, xj is going here, both points are intersecting. Okay. Then axis xj is perpendicular to the axis zj minus 1. If you look at, both are perpendicular. This is coming this direction, this is going this direction, now mutually perpendicular together. The result is only 4 parameter. These two things normally we will not consider. Remaining 4, it will they are considering. Result not only 4 parameter, not 6. The link frame is not necessary on the link. So here, based on these two things, these two link, we are considering only 4 parameter. Let us go to what are the parameter. If you want to make a, DH convention, convention means if you want to represent, you have a 6 variable, 3 rotation, 3 translation. DH parameter collapse 6 variable into 4 link parameter provided based on the DH theory. What are the things they are considering? A, alpha, D, theta. Okay, A is the link. Alpha is twist of the link. So these two, it will be constant. These don't change unless you reconfigure the robot. Link is there, link it will not change. So if you want to increase the link length, then only we are putting new one. Otherwise it will, we will follow the same thing. Then the d is the link offset, that is a prismatic variable, linear movement. And this is the rotary variable, theta is the joint angle, link offset, right? The joint angle, these two. Here we are putting symbol for all those things. Theta is the rotation about z axis, d is the distance on the z axis, a is the length of the each common normal joint offset. That's what we are discussing here, joint offset. And alpha is the angle between the two successive z axis. Okay, normally called twist. Here theta and d are joint variable. Theta and d are joint variable. Now, for example, if you want to take a two link, right, a two link representation, if you want to do it, so theta, d, a, alpha, four parameters are given here. You can describe it. Remaining d and alpha both are 0. So here you have a parameter available, length of the link, a1, a2, and angle with respect to link 1 and link 2. So normally angle q1, q2. So they wrote q1, q2, and length of the first link a1, second link a2. So a1, a2 is clearly given. Remaining two are 0. Now suppose if you want to put it into the DH representation into the form 4 into 4 matrix, if you want to make it here, if you take a if you take a reference, one reference frame to the next, always this is the best thing to do. This include two rotation, two translation. Look at the sequence: rotate, translate, translate, rotate. RTTR. So this is the way we will explain simply in class. Rotate about the z-axis. This is a coplanar. Then translate along zn axis at distance of dn plus 1. Then translate along the xn axis, distance of a n plus 1. Then rotate x n plus 1 angle of alpha n plus 1. So this is the requirement here. For this, if you want to put it into the convention, means it's a representation. If you put a homogeneous transformation for representing given here, the product of 4 basic transformation. So rotate into, translate into, rotate. Multiplying all for this, you will get the clear representation. So this is available like AI, rotation, translation, translation, rotation. With respect to which axis it is clearly given. Okay. So now rotation, the rotating about z-axis. So already we given, right? Some values are given here. And the translation, it is given here, only distance with respect to z-axis. And again, translation with respect to x. X you put A, remaining thing you leave the matrix as it is. Then again, rotation with respect to z-axis. Rotation with respect to z-axis about x. So x means it will come here, right? So this is the value already we given here. If you go for matrix multiplication, you will get this matrix. Okay, this matrix. So this is the DH representation of homogeneous transformation. Next, I am coming to another important topic of Jacobian matrix. So, what is it? How it is connected with robot? Right? Here, the students, I know very well. You are belongs to computer science department. You don't have any prerequisite about the complete robotics. Therefore, I am giving the for explaining fundamental. I am giving this slide. So, Jacobian is the used in change of variable in the multiple integral. Jacobian, it is a basically determinant, almost it is like a constant. It is used to transform the variable into one coordinate from two variables in another coordinate frame. So for transformation, here generally the real use of Jacobian matrix to find the velocity of an end effector. So end effector velocity, it is important. Previously we said velocity is important component. Okay, for that the Jacobian matrix is very important. We use a notation like chi to represent velocity at end effector in the base frame, and the velocity of the end effector at the base frame has two components. One is linear and angular. Linear velocity you represent into v, angular velocity you represent of omega. The linear velocity you have three component x, y, z, right? Linear velocity, linear movement from with respect to x-axis, y-axis, z-axis. Similarly, angular movement, the angular velocity you have with respect to rotation about x-axis, y-axis, and z-axis. Here, if you put it into the form v naught n naught, linear velocity and angular velocity, we consider parameter q as a generalization of joint variation. Revolute joint is q is theta. The prismatic joint means linear joint. It's a displacement of d. So q dash is a time derivative. Q dash is the one of the column. So for articulated manipulator, we have three revolute joint. We have to write theta 1, theta 2, theta 3, right, with respect to q dash. Similarly, q dash for prismatic joint, right, theta 1, theta 2, and another one, it is taking a linear joint, what is called linear movement, which is already described called d, distance d. So now come to the Jacobian formulation. So what is Jacobian? So we clearly explained how we are using into our robotic system, robot system. That is important here. So here Jacobian, which relates the dynamic relationship between two different representation of a system, right? Two representation. For example, if you have a two-link robotic arm, there are two obvious ways to describe current position: end effector position and orientation, end effector position and orientation, and set of joint angle. The Jacobian for this system relate how movements of the element of Q causes movement of element X. So Jacobian as a transformation matrix for the velocity. So now here velocity already we discussed. Jacobian is a set of partial differential equation. Here you need to recall your partial differentiation equation. Conventional differentiation is different. Now we are using partial differentiation. Here Jacobian matrix J equal to dx by dq. So this is already we said it is a velocity displacement by the time vector. The bit of manipulation for get a neat result, we are taking Jacobian matrix dx dq is there. Dx dq leave it. You add delta t and delta t. So this both will get cancelled. Again you will get it. So finally dx by dt and dq by dt, right? Finally, you will get it like this. So x equal to, you will get j into q, you will get it. So dq by dt, dou q by dou t equal to q, and this j constant, it is already available. Okay. So now here x and q represents the time derivative of x and q. Next, the Jacobian matrix, how they are doing dx by dt, dy by dt. Here delta, so from matrix we are writing r cos theta. So this is the linear moment, r cos theta, d by dr and dr by dt. So this dr we are adding in between. Okay, dr, it will get cancelled. Again plus another angle delta r cos theta, d theta, right, dt. Finally, you will get it dx by dt, it is called x dot. Dx by dt represents x dot. Here cos theta you keep it as it is, and again r dr by dt it is r, so remaining all of them. Okay, and minus. So here, why they are putting minus means putting partial differentiation for cos theta is minus sin theta. Therefore, this minus sign is coming, minus sin theta. You keep it, car is a constant. Dou cos theta by dou theta, it is called sin theta, and d theta by dt, it's a theta dot. Similarly, y, same thing, sin theta, dy by dt, make it y dot, and sin theta, you keep it as it is. Dr by dr, it will get cancelled. Dx by dr, sorry, dr by dt, r dot. And similarly here, you take r, it's a constant outside. Dou theta by dou sin theta by theta, you will get cos theta, right? Cos theta. D theta by dt is equal to theta dot. So this one we are putting into the representation. So you put a inside input x dot y dot. So therefore you will get it r sin theta cos theta, r sin theta cos theta, and r cos theta into sin theta. So here this is the way you have to represent. For this, if you want to take that theta dot t dot, sorry, theta dot r dot is the constant values. So finally, if you want to make a Jacobian r sin theta, r cos theta, sin theta, this is called J Jacobian matrix. Theta dot r dot is there, where J is the Jacobian matrix. So this is the direct equation. So for real-time application, straight away, once if you know the angle, straight away you can apply angle theta and r value. Straight away you can apply. You estimate the Jacobian matrix. Next, I am coming to the second half of the unit number 4. It is a trajectory planning you have. If you take introduction about trajectory planning, it is associated with two things. It is with the path planning and the trajectory planning. So, of course, trajectory planning straight away we can't do. This is highly connected with the trajectory planning. So, first we will understand that the path and trajectory planning means the way that a robot is moved from one location to another location in a controlled manner. The sequence of movement for controlled movement between the motion segment in a straight line motion or in a sequential motion. This require use of both kinematics and dynamics, the robot. So this is about introduction. So now we need to understand the difference between what is path planning, what is trajectory planning. So if you go there, path versus trajectory planning, path is a sequence of robot configuration in a particular order without regard the timing of this configuration. So here path planning, we are not bothering the timing. This is the important thing we need to understand. The trajectory means it will be connected with the timing. Let us say it is concerned about trajectory is concerned about when each part of the path must be attained, thus specifying timing. So timing is important. This is time based. Sorry, this is not time based. This is the time based. Next, I am coming to the overall robot motion planning. If you want to control, okay, path planning, trajectory planning, we understand what is what, path planning connected with what, trajectory planning connected with what. If you put overall robot movement, robot motion planning, first we have to do the task plan. We understand the task, whether we need to make a linear movement, rotary movement. For a task means pick and place, right? Or loading, unloading, different tasks. So this is what I asked the prerequisite for the robotic application. So task, it may be pick and place, that is a linear movement, or sometimes the pick and place, it will be angular movement. What is a task? We need to understand. First, we make the task planning. From task planning, then you will get an action plan. From the action plan, you will get the path plan. From the path plan, then if you are putting all the time component into that, you can make a trajectory plan. That plan we are giving to controller. That kind of based on the plan given, the robot will function. So again, robot, it will make a contact with environment. It will take a feedback. Any change is required. Again, that will comes to controller. Controller will revise the plan, revise the trajectory plan, and give an input to robot. Robot will perform. In general, path planning is completely geometrical. It is issues about obstacle and avoidance, shortest path. So this is what our major goal, right? Shortest path, obstacle avoidance. In case of trajectory planning, interpolate, approximate the desired path by the class polynomial function. Generate a sequence of time-based control set point. This is important. A task is there. How long it will take to complete that particular task for the control of manipulator from the initial configuration to destination. So here we can clearly understand what is a time-based, what is non-time-based. Coming to trajectory planning, if you take a problem statement, turn a specified Cartesian space trajectory PE into approximate joint position reference value. Here input is you have a Cartesian space path. Okay, and the path constraints including velocity, acceleration limit, and the singularity analysis. Here output is we need to identify the joint position velocity reference value to send to controller. What is the joint position? What is the velocity reference? So these are all the output we need to estimate, and that will be given to the controller. Robot controller means robot controller. They are talking. In trajectory planning, two inputs are required. One is path specification. We clearly make a path planning and specify. And here path constraints. So here we are adding all the time constraints, everything. From this, the outcome of trajectory planning, it will be the giant space and Cartesian space. Here you will get it a sequence of control set points along with the desired trajectory. So we clearly understand that what is trajectory planning, what is the input, what is the output. Here we need to understand the difference between the joint space versus task space. Joint space description of motion to be made by the robot by its joint values. Joint value means angle or something. The motion between 2 points in joint space is not predicted. The task description, motion between 2 points is known at all time and controllable. It is very easy to visualize the trajectory, but it is difficult to ensure singularity robustness. That is important. Now let us go for task planning. A typical example task planning. These sketches are clearly available. Suppose if you make a sequential motion of robot, see here a single motion, sequential motion, both are there. If you make a sequential motion of the robot, initially robot position is at the middle. From middle it is coming to A and going to B. Okay, sequential motion. There is some sequence 0 to A to B. Okay, this is a sequential motion. Look at the path, it is a straight line. Okay, this is the one task planning. For example, Cartesian space trajectory, the trajectory specified in the Cartesian coordinate may force the robot to run into itself. For example, here you look at movement is linear. And again, P trajectory may require sudden change in joint angle. That the joint angle here initially, originally it will be available. Here, what is there? Some changes, angle changes. So this is the way we have to plan the task. Trajectory planning now, there are two things, point-to-point motion, continuous motion. Teach initial and final point, intermediate path is not critical and computed by the controller. Here, point-to-point motion, just initial and final is required. So from initial it will start and stop at once reaches the final point. The application, typical application is moving parts. Moving parts means material transfer. We studied in application. So this is what I asked the application prerequisite to better understanding of trajectory planning. Spot welding, automated loading and unloading, pick and place. Here they are using point to point. In between, you need not bother about anything. Whereas continuous path motion used when there is a need to follow a complex path through 3D space, possibly at high speed, like spray painting, welding, polishing. So this kind of thing, the continuous path motion is important. These points generally taught by manual lead through with the high speed automatic supply. Next, I am going to different types of movement. The point to point movement. Simple point to point smooth trajectory, few constraint on the lift off and set down. There are three ways a manipulator can move from point to point: slow motion, joint interpolated motion, and straight line motion. SLEW, slow motion means uh, all the joints move to their required new position as quickly as possible. All axes begin motion at the same time, but it arrive at their destination at a different time. This is generally result in joint wear and unpredictable arm motion. So generally in robotic system, we need to avoid unpredictable movement because you are using actuators and other thing. And the joint interpolated motion requires controller to calculate which joint will make a longest arrive at its destination and slow other joints downward accordingly, joints down accordingly. A separate velocity is calculated for each axis. The manipulator motion is generally smooth and wear is reduced. So the one out of the joint, that is important. In a straight line motion, the particular case continuous path motion, it is coming, it is acted. This already we discussed. This is used at the material transfer or pick and place application of robot. For example, if you want to point to point motion, if you want to describe in the with respect to time, for example, joint angle and time. Initially, what is at the joint angle and time? And the lift off. Once lift off, it is started. Then slowly it is keep on increasing. Joint angle it is keep on increasing. You can know initially angle is less. Joint angle keep on increasing, and again what happened? The height set down. This is the final position. So joint based trajectory for a single point using a point to point motion. And again lift up and set down points provided for satisfying acceleration and constraint. You please come later. Uh, Next, I'm going to cubic polynomial trajectories. So here, if you have a single joint, that is a 1 degrees of freedom. 1 degrees of freedom means possible degrees of freedom is one. Degrees of freedom means possible way of movement. Single joint, if you consider, we know theta 0 and theta f. That is the theta starting, theta final. That is initial angle, final angle. We also know theta dot, theta final, theta dot, that represent velocity. We want to find theta of t, theta dot of t, and the theta double dot of t. This is always represent the acceleration also. Here theta dot t is equal to dou theta by dou t with respect to t. This is t double dot means dou by dou t theta dot t. Suppose we have a four constraint. Let us try a cubic polynomial. Theta t equal to a naught, a1 t, a2 t square, a3 t cube. This is the way we have to represent it in terms of polynomial. In cubic polynomial, the uh, to determine the coefficient, we need to look at our boundary conditions, namely, what is the position at t, velocity, position t after final. So that is the initial position, initial velocity, final position, final velocity. Here theta is already this equation described. Theta dot t you will get a1 because this becomes 0. Just put a differentiation. Okay, a2 2a2 into t, right? T square. Here 3a cube t square. So you just put a differentiation, you will get this. Now the plucking in this, we get theta naught equal to a0, theta final equal to theta of 0, theta dot of 0, tf a2, everything. Here theta dot of 0 is a1. So here you solving a2 and a3, solving a2 and a3, you will get a2, you will get this equation, a3, you will get this equation. Then finally, so the a naught, a1, it is already there. So a2, a3 equation it is given. If the initial and final velocity is 0, then you substitute the value for 0. Here you will get a2 value is this much. You will get an equation like this. A3 is like this. So finally, the acceleration is given. Acceleration means double theta t, 2a2 into 6. Here you just put a differentiation of this for here. This becomes 0. Here you will get 2t a2 and here 6. So that's what they are discussing here, 6a3t. So finally, if you substitute your values, you will get it like this. So this is the acceleration. Here minimum torque trajectory. So is theta dot. This equation is good solution. Solve following minimization problem. So this is available. This is a task available. We can do it as a case study or some other thing. Now I want to talk the quadratic polynomial trajectory. The cubes allow us to define position and velocity at each location in a trajectory. However, the acceleration is discontinuous. You know, the acceleration means variation in speed. If goes constant speed, their acceleration will be 0. If you want to specify the acceleration, we would need a quantic or order of 5 polynomial. So 5 order is required. So they are describing like this: a naught, a1 t, a2 t square, a3 t cube, a4 t4, a5 t5. Use this initial and final position, velocities and acceleration as our boundary condition to solve the coefficient. So previously A1, A2, these are all the coefficient, we got an equation. Suppose if you want to go for the five polynomial, here it is clearly available. Theta, omega naught, alpha, theta f, w f, everything. And here you have to represent the matrix. So just put your coordinate like this. Okay. Then finally, this is the value of the coordinates value. A1, A0, A1, A2, A3, A4, A5. Now the pick and place operation. What is the path profile? Path profile. What is the velocity profile? What is the acceleration profile? So this path profile already we have seen. Okay. Now in order by considering this, so initially, if you talk about speed, initially it will be zero. Once if going to lift off, that is a force. The velocity it will be more. Then again what to do? Lift up and set down. It will be constant speed. Again what to do? Speed will come down. So initially increasing speed, then constant and coming down. This is the velocity profile. Whereas acceleration, whenever speed variation is there, it will count. So you will get an acceleration. It is increasing, then reaching one particular acceleration. That means constant velocity, constant speed. Wherever speed is constant, acceleration will be zero. Acceleration will be constant. So again, you will get a down movement. A down movement always it is called a deceleration. So again, same thing. Okay, this is the acceleration profile for pick and place operation. Pick and place means the application I clearly described, the parts moving from one place to another place. Next, previously we discussed the boundary conditions for setting for real-time application. If you want to do any project or any case study, this boundary condition is important. What is the initial position, initial velocity, initial acceleration? Lift-off position, continuity in position at T1, continuity at velocity at T2, similarly acceleration at T1. Set down position, continuity position at T2, right? Continuity, velocity, position, velocity, acceleration. Then finally, final position, final velocity, final acceleration. So totally this 14 boundary conditions are very important. So this will be required to control any applications. Here the known parameter in this system is the position. It is given. Velocity normally 0 at initial position. Acceleration normally at 0. So intermediate position, lift up and set down position it will be given. Velocity continues with the previous directory. Acceleration it will continue continues. The acceleration with respect to velocity. For example, a fan it is running from when switch on the fan. It's initially the acceleration is 0. So until reaching steady speed, it will rotate continuously. So once reaching the rated speed, then it will rotate constantly. Therefore, no acceleration is there. Whenever switch off the fan, then acceleration it will come down. What is called retardation. So negative value of acceleration is retardation. Now I am coming to trajectory planner interfaces. What are the elements if you want to apply for project work or anything? Trajectory planning interface is important. Functional robot units, you have a trajectory planner is there. External sensor is there, so that to give an input to trajectory planner. If any obstacles or anything comes from environment, the external sensor it will sense and give to the trajectory planner. And again, you have a task planner. So previously I given task planner is a basic input to the trajectory planning. Then it is going to control unit. Then it is a robot. So robot environment, you have a sensor. Robot, you have a internal sensor that it will guide properly. For example, you look at the robot action is described sequence of poses or configuration. What is called a trajectory planning. That basic input is required. And again, reference profile values continuous or discrete continuous. The robot is continuously doing or in between any stop and do like this, or any obstacle comes wait to cross that object the obstacle and do like this. Next time, straight away go to the collision detection and avoidance in a robotic system, how they are doing. So this is the last topic of the unit. Collision detection and collision avoidance. It is the collision detection is the most important factor of path planning. Without automatic collision avoidance, the robotic workcell must be engineered to be collision free, or suboptimal path must be chosen by the human programmer. Either automatically we have to do, or we have to do it through the human programming, robot programming. We have to control it. Here, why the collision? You people will ask, what will happen if collision comes? So, robot, for example, it is carrying a machine and moving one place to another place. Uh, in between, if it hits, so an object, suddenly a new machine or some repairing fellow, they came, they is crossed. Then both are collision together, it become a big accident. Machine will damage, the people who are handling, he will die. So many problems are there. So there, therefore, this important thing. One of the major use of robot is to reduce the human power, to reduce the human risk. So again, collision comes. People who is handling near, who is standing nearby machine, who is so that fellow he will die. So again, it become against. Therefore, the collision detection and the collision avoidance, it is a very important part of the robot. The local collision detection is important when moving through an unknown or uncertain environment. These allow for feedback to the planner and a halting path which contain collision. The global collision avoidance may be done for planning path which should avoid the object. Something they will do local and global, or no collision. This will be there. For example, without collision is there. You have a initial point, end point. In between there is a obstacle is there. Initial point, then it will make a collision, and again it is going. Normally we should avoid. So if collision avoidance is not there, and again collision avoidance is there. If it is a local, initially it will start through sensor. We will get it through sensor. We will go very near to collision point, and again we will take a diversion, and finally it will reach. So we will get a local system. We will get an alert, and we will do the collision avoidance. If it is a global system is there, the collision point already it will be predicted. So your path, it never near, very near to the collision point, it will avoid. Okay, this is the way the collision systems and the collision detection and avoidance it is running to ensure the safety of operator, safety of labor within the company. Then motion of obstacle. If obstacle, suppose it is moving, then what to do, right? There are three conditions. One is static. Statics means non-moving, deterministic, and randomly. The obstacle determine periodically it will move. For example, 1 minute rest, 1 minute movement, like that it is going deterministic. Random means it does not know. Randomly it will come and do. I am going to explain a typical example here. Problem of robot motion. If turning is needed to avoid the collision. So end effector is there. No, we have to turn and move. For example, here you have two passages there. In between that, robot should carry robot end effector. It will carry the product. Okay. Uh, we have that blue color blocks are there. No, it will be very a little gap between the two blocks. Then the obstacle comes means suddenly what happened? The gap between the two blocks, blue color blocks, are closed. That time what to do? You have to initially your parallel movement without doing anything. If it is there is no movement, static. Suppose the movement is there like this, movement is there like this, then what to do? We have to go for turning in definite points. It will come here, sense the gap between these two. Then what happened? Change the position by 90 degree, turning by 90 degree, and inserting through the obstacle. Therefore it will reach the end point. Okay. Whereas if it is a continuous turning is there. Here, automatically it will change. So continuously it will go. So whatever minimum gap is there, through that they will set the path. So path planning means they are a block line. They are putting no where the direction what we are where we are going. Right. This is what. So with this, I'm concluding unit number 4. I hope all will understand. I hope I explained the unit number 4 with sufficient example. So with this, I am closing. Thank you very much for watching this video.